Okay, good morning. So today we will start discussion on size distribution function and governing equations. Okay, so I have given you slight idea about the size distribution function in the previous class as well. So particularly, as I told you that if we deal with the granular flows, okay, where we have lot of solid particles which are dispersed in the gaseous phase, or the other situation could be that air bubbles are dispersed in the uh, liquid phase, or liquid droplets are dispersed in the gaseous phase. Okay, so then we will be finding that large number of these particles will be present within the system. Now of course the sizes of particles will be can vary over the wider length scales. So what we need to do, we need to characterize our system that what distribution of different sizes is present in the system. For that purpose actually we go for size distribution function. So what we do, let us consider that if I have some container, and in this container I have some granular particles of total mass m. Okay, out of this, if I can say that m1 is the mass of particles having diameter say in the range of 1 micrometer to 10 micrometer. Okay, likewise m2 is the mass of particles having diameter 10 micrometer to 20 micrometer. Okay, so likewise what I can do, by using some mechanical sieve arrangement, if I can segregate the particles within this band, and then if I take their individual weight, so I will be knowing the values of m1, m2 and m3. Okay, now if I define one more variable f as mass fraction. Okay, so F I am defining as mass fraction, where m1 divided by total mass of this combined particles is capital M. So that can be my F1, which will be mass fraction of particles having sizes in between 1 micrometer to 10 micrometer. Okay, so once we have this type of characterization based on the size available in terms of mass fraction, what I can do, I can plot the fraction f as function of particle size. So say particle size is starting here from 1 micrometer, this is 10 micrometer, this is 20, 30, 40 or so. Okay, so now say from 1 to 10 I am having fraction value somewhere. What will be the scale of this? It will be from 0 to maximum, it can be 1. Okay, if say entire sample is actually constituting of one particular type. Okay, so and overall this fraction has to be, let me consider it 0.5, because overall the sum of all fractions has to be equal to 1. So likewise what I can do, can I plot this type of histograms? Okay, so this type of histograms I can have, which will be giving me the corresponding individual fractions. Okay, now if I take midpoint of all the histograms and if I join this midpoint, what I will be getting? It will be a curve. Okay, now if I fit this curve using some mathematical function n of f, then this particular function is something which is called as size distribution function. Is this point clear? Okay, so a mathematical function which will be fitting all this distribution of the particles in different sizes, that we will be calling as size distribution function. Now over here what I have done, I have divided the particles based on their masses. Okay, mass of a particular set divided by total mass, so that is based on the mass fraction. So instead of the mass fraction, you can also divide these particles based on their volume, then it will be becoming the volume fraction. Okay, and you can also divide the particles, say if you consider that your particles are of homogeneous shape of the particles is same. Okay, shape is not changing, though sizes are different, but shape of particle is remaining the same. So in that case, you can even define this size distribution function in terms of either in terms of the radius or diameter of the particles as well. Okay, so now one more similar function is something which is called as cumulative size distribution function. So can you tell me what will be there in cumulative size distribution function? Yes, so for example, if I defined earlier n of f as my size distribution function, in case of cumulative size distribution function, I will be considering integration from 0 to f and then n of f df. So over here, all the particles which are there in the previous band, when I will be considering the next band, then I have to take sum of the previous one. Okay, so cumulative one, let me call it as say n star of f. So n star of f, if I plot, what I will be getting? Initially this was the value, some value, then second value will be sum of previous one and this somewhere over here. Then next will be, this will also be added. Okay, so once this is also adding to this, it will be becoming high, and then finally slight delay, but overall number should increase. Somewhere over here. So this will become my cumulative size distribution. Okay, now one important point, in this function, this is not behaving properly. Yeah, so here if you see over here, what is it is representing, it is representing the fraction only. Okay, now in this fraction, what will be the lowest value and what will be this highest value? This has to be equal to 1, because ultimately in cumulative we are summing up each and everything. Okay, so once we are summing this up, if I consider the fraction of 0.5, okay, so corresponding to fraction of 0.5, whatever be my particle size, that particle size is nothing but my median particle size. So in statistics, whenever we calculate the, we use the statistical averaging, then we define different kind of averaging. If we are simply taking the arithmetic average, then we say the quantity as mean particle size. Okay. If we prepare this cumulative size distribution function. Corresponding to cumulative size distribution function, if I consider the mid fraction 0.5, corresponding to that, whatever the value of size I will be getting, that will be my median particle size. Okay. Now, if I take, so say f star was my cumulative fraction. Okay. Now, if I do this thing df star by dd, where d is particle size and f star is cumulative fraction. Can you tell me how the curve of df star by dd will be looking with d? So you can see in your curve of f star, what you have? Initially slope is less, then in between slope is high, and again slope is decreasing. Okay, so it means that initially it will start like this, then it will be having peak slope, and once again it will fall. Okay, so corresponding to this peak, whatever the d you are getting, this is your mode. Is this one clear? Now, whenever we do calculate or do characterize our sample, as I told you, we are having large number of possibilities to characterize the sample. We can define its arithmetic mean, we can define the geometric mean of the sample, we can define median, we can define mode. Likewise, there can be other plenty of options. One of these options is called as surface mean diameter. Okay, and surface mean diameter is one of the important parameter whenever we talk about the hydrodynamics of the system, whenever we talk about the heat and mass transfer from the system as well as its hydrodynamics. Okay, why? Because when we see our heat and mass transfer which is taking place from the particles, that will be taking place through its surface area. Okay, so that's why characterizing the surface mean diameter will be important. Now, how to determine surface mean diameter? So what we can do, we can now characterize particles based on their surface area. Say I have n1 number of particles having surface area S1. Okay, so n1 over here is number of particles having surface area S1. N2 as number of particles having surface area S2, N3 as number of particles having surface area S3. Okay. Now in this scenario, what will be happening if I have to define the surface mean diameter d bar S? That will be becoming equal to N1 into S1 d1 plus N2 into S2 d2 plus so on up to divided by N1 S1 plus N2 S2 plus N3 S3 likewise. Okay. So the particles which are having S1 surface area, their corresponding size is D1. The particles having surface area S2, their corresponding size is D2. And particles having surface area S3, their corresponding size is D3. Okay. So likewise, if I do this type of averaging, this is called as surface mean diameter. And surface mean diameter is an important parameter. It is also called as Sauter mean diameter. Okay, this surface mean diameter is also called as Sauter mean diameter, and it is an important parameter which we use when we characterize our hydrodynamics and heat and mass transfer from the particles. Okay. Then another way of characterization can be mean surface diameter. Now you have to understand the difference. Mean surface diameter. Again the situation is identical. I am having n1 particles of surface area S1 having sizes D1. N2 particles having surface area S2 but sizes D2. Okay. Likewise, let us make one assumption that shape of all particles is identical. So shape is identical, only their sizes are different. Okay. Now, if shape is identical and only the sizes are different, then if you have to characterize this surface area S1, how you can write? Some, for example, if you have a sphere, what is the surface area of sphere? 4 pi d square or r square. Okay. So likewise, here what will be happening? I will be having some constant factor, and that constant factor will be multiplied with square of the size to characterize the surface area of the particle. Okay. Now if I consider that among all these, say ds dash bar is my mean surface diameter. If this is my mean surface diameter and n is the total number of particles, then I can say the total surface area of the sample in terms of mean surface diameter can be n into k into ds dash bar square, and this has to be equal to n1 into what? Particles having surface area S1, so S1 can be written in terms of k into d1 square plus n2 k into d2 square likewise. So from here I will be getting that d dash s bar will become equal to simply n1 d1 square plus n2 d2 square divided by n, and this entire power, if I remove 2 from here, then 1 by 2. Shape of particle is identical, not spherical. Over here I am not saying the diameter, I am saying size. Okay. So size means whenever you have different random type of shape, then we use some parameters to characterize its size. Okay. So how to characterize the random shape of the particles, that I will discuss you in the subsequent lectures. Okay. I am not saying over here that all the particles are spherical, but the assumption is that shape of particles is identical. If shape of particles is identical, then in characterizing the surface area of the particles, this constant multiplying factor will be remaining the same. Is this one clear? So this type of diameter is called as actually mean surface diameter. So likewise we can define different ways, but the important one is either surface mean diameter or mean surface diameter, which typically we will be using for hydrodynamics and heat transfer applications. Okay. So here you can see that this is number density distribution function NR for different particles based on their radius. Okay. So basically, as I told you, that if I write NV into dV as my particle size distribution function, it means that this NV represents the size of particle having diameter in between V to V plus dV. Okay, is this point clear? So NV over here, if I write NV as my size distribution function, then NV will be representing the number of particles having diameter in between V and V plus dV. Okay, so this is a sample size distribution function for small bubbles which are present in 3 water tunnels in the ocean. Okay, so here you can see this is the number size distribution function and this is radius. So here you can see that in 3 different tunnels how the size distribution function is varying, and one important point you can observe is whenever the radius of the particles is small, then number of bubbles existing are more. and for large sizes number of bubbles existing are less. One reason could be because the smaller bubbles, because of the surface tension, can stay their entire fluid volume, can hold their entire fluid volume. Wherever if you have larger sized bubbles, then if some surrounding flow is disturbing these, then larger sized bubbles can break into smaller sized bubbles. Okay, so that is the reason whenever for fluid particles, particularly for the bubbles and droplets which are subjected to some surrounding fluid motion, when you will be determining the size distribution function, majority of the time you will be finding that their number will be high towards the lower sizes, and in larger sizes their number will be less. Is this one clear? Now this is the number distribution function again, and this is distribution function of bubbles in freshly poured guineas, and it is once you have poured this guineas in the glass, and after the 5 minutes you have counted the bubble distribution function. So here you can see this is freshly poured distribution, and this is the distribution after 5 minutes. Do you know what is this? Guineas. Guineas is beer. So typically in Ireland this is very famous, and they say that it tastes like coffee. So here you can see that this number distribution function, when you have freshly poured, corresponding to that the number in lower sizes were less and the number in larger sizes were more. Okay, but when you have seen the distribution after 5 minutes, then the number in the lower sizes has stayed almost the same, whereas the number in larger sizes has decreased. What is the reason? So typically if you have a glass of water, and there you can see that when you pour water into the transparent glass, initially you can see a cluster of bubbles is actually air bubbles is getting entrapped, and then immediately, because in water density difference with the bubbles is high, so there what happens, immediately these bubbles rises to the surface and disappears from the water. Okay, so over here what will be happening in the glass of the beer, whenever you are having larger size bubble will be having more tendency to rise in the upward direction because of the buoyancy effect, whereas the small size bubbles will not have enough buoyancy to rise, and these will almost try to stay within the medium. So that's why after some time also you can see the distribution function in larger radius is almost remaining unchanged, and in in smaller radius, but in larger size it has decreased significantly. Okay, so this is typically the cumulative size distribution function. So n star v star is integral from 0 to v star nv into dv. Okay, now here you can see what they have done. So typically this volume, if I consider that particles are of identical shape, then volume can be replaced with some equivalent radius defined for that particular shape. Okay, so one size distribution function is given for various coal slurries over here, which are designated by symbol C, D, E, F, G, and n star R is actually divided. What is n star R? Can you tell me? N star R will be integral n of R into dr from 0 to R, and then there is n star infinity. What will be n star infinity? Integration from 0 to infinity nr dr. So when you are doing integration from 0 to infinity, what it means? It is taking into account all the size distribution presented in the sample. So it means it is taking into account the complete slurry number. Okay, and when you are fixing this to some value of R, then it will be taking only the fraction which is having sizes from 0 to R. Okay, so it means this n star R will be divided by n star infinity, will be representing nothing but the number fraction. Is this point clear? This will be number fraction. Okay, number from 0 to R divided by total number of particles present in the system. So in this number fraction you can see that initially when sizes are low, then value of this fraction will be less. But when you keep on increasing your R, then your numerator will keep on increasing. Denominator is same, numerator will keep on increasing when you are increasing the R. So once your numerator is increasing, your fraction will keep on increasing. So that is the reason when sizes were low, then the value of fraction was close to 0, and when you are increasing the value of R, fraction is actually trying to approach to 1. Is this point clear? And for a particular type of slurry where fraction is becoming 1, you can say that here sizes present in that slurry are only within this range. Whereas sizes present in this larger, particularly in this C slurry, is actually within this range. Because beyond this range, fraction is almost becoming 0. Is this point clear? All are able to interpret this graph, what I have discussed? Now, and if you have to calculate the median size particle for all these slurries, what you can do? Corresponding to volume fraction of 0.5, you can check the size, and you will be finding median size distribution function for median size of the particle for all the slurries which we have under consideration. Okay. Now, so what is the benefit of this? Can you tell me what is the benefit of this distribution? The benefit is, whenever you will be talking about the flow, we have to decide whether the relative motion between the particles and the surrounding fluid are important or not. Okay. So if you have a larger sized particle and flow is happening, if you drop a larger sized particle in the flow, what will happen? It will try to start flowing with the flow. Okay. But in order to acquire some steady state within the flow, it will take some time. Okay. And if you drop a smaller size particle, its response to the flow will be faster. It will try to acquire the dynamics of the surrounding flow easily. Okay. So, whenever later on I will be giving you some idea about the turbulence present in the multi-phase systems which are having particles available. Okay. So, if the sizes of particles are below certain critical limit, then if any fluctuations, turbulent fluctuations are present in the system, then particles try to simply follow the path of these turbulent fluctuations and they try to stabilize the flow. In some situations where particle sizes are larger in comparison to the flow hydrodynamics time, in that case what will be happening? Particles will not be easily adjusting to the flow, and by the time they will try to adjust, they will reach to some new surrounding flow situation. Okay, so this is something which you will be able to understand after a few lectures, because we will be talking about hydrodynamic response time of particle and thermal response time of particle when it is present in the surrounding fluid. Okay, so there this idea will be more clear, but overall point is that this size distribution function, for the time being you can simply understand that it is nothing but giving you some idea about the range of sizes in the range of sizes of particle presented in particular center. Okay. Now one parameter is defined over here, alpha d. So do you know from the previous lecture what is the definition of alpha? Volume fraction. And when it is referred with d, it means it is pointing towards the volume fraction of dispersed phase. Okay. Now you can see what I have done. I have done integration from 0 to infinity and NVdV. What is the meaning of this? If I don't use first V, only do integration 0 to infinity NVdV, it is cumulative distribution, and when I am using 0 to infinity, it means it is representing the total number of particles present in the system. If that I multiply with V, what is V? Volume of particles. What it will give me? Number multiplied by volume. Total volume of particles present in the system. Okay. What is total volume of particle present in the system? If I take overall system volume as unit volume, it will be volume fraction. Is this point clear? So what I am saying is NV is the number. When NV is multiplied with V, what it represents? It represents volume of particles. Is this clear, or should I explain it again? Let me explain it again. Let's say V1 volume of particle, if it is there, then corresponding size distribution function will be NV1 into dV. If V2 is the volume of particle, corresponding to that distribution function is NV2 into dV. Now, what will be the overall volume of these particles? V1 into NV1 dV. What will be the volume of these particles? Okay. If I take sum of all these and integrate this from 0 to infinity, what I will be getting? Total volume of all the particles. Okay. So total volume of all the particles, if I am containing inside a system of unit volume, then it will be becoming simply my volume fraction of the particles. Okay. And as the particles we are considering as the dispersed phase, so this is nothing but my overall volume fraction. Is this point clear? Then if assumption is, if say all the particles are of spherical size, then it will be simply becoming equal to pi by 6 into dq and dash. Okay. Now this is one formula. djk is equal to integral 0 to infinity dj into n dash d dt divided by 0 to infinity dk into n dash d dt 1 by j minus k. So this is a generic formula, and the way I have previously calculated surface mean diameter, mean surface diameter, okay, all these diameters can be obtained using this formula. So for example, if you have to calculate surface mean diameter, which is also called as Sauter mean diameter, then you will be taking j equal to 3 and k equal to 2. What you will be getting? d32 equal to integral from 0 to infinity d divided by 0 to infinity whole power 1 by 3 minus 2, which is 1. Okay. So now you can see the term in the numerator is actually representing cube of d. It means it is identical to volume. Term in the denominator is d of 2, identical to surface area. Okay. So typically, whenever a particle is present in the fluid medium, one will be body force. Body force will be identical to, body force will be proportional to volume of the particle, and other will be surface forces, pressure, shear stress, etc. will be causing some surface forces across the particle, and surface forces will only be applicable at the surface area of the particle. Okay. So whenever we will be analyzing the hydrodynamics of the particle in a fluid medium, then because we have to do the balance of body and the surface forces, so we should use Sauter mean diameter, which will be a good representative for this type of problems. Whenever we will be simply doing the heat and mass transfer, we are not concerned about the hydrodynamics. then what is our interest? Our interest is only how much energy or mass exchange is happening across the surface area of the particle. So there, instead of using the shorter mean diameter, we can simply go for mean surface diameter, which I have defined previously. Okay, is this one clear? So if you have to calculate mean surface diameter, then in the numerator what you require? Power of 2. So j I will be taking 2 and k I will be simply taking equal to 0, because my only interest is calculating the mean surface diameter. Is this one clear? So likewise, we can also take mean volume diameter, volume mean diameter, depending upon our requirement. So for different systems, whatever is the requirement, based on that we can actually choose one particular type of system for characterizing the overall mean of the sample. Okay, and this is mainly depending upon the application which we have in hand. Okay. Now comes equation of motions for multi-phase flow. So all of you know about equations of motion for single phase flow. So if we have adiabatic single phase flow, then we have to solve continuity and momentum equation. Okay. Momentum equation is a vector equation which will be having three components in, if we have Cartesian coordinate system, then in x, y and z directions. Okay. Important point is, whenever we write momentum equation, then in momentum equation we have some stress terms. Okay. And these stress terms can be easily represented in terms of viscosity of the fluid medium. If fluid is Newtonian, then viscosity for that particular fluid will be constant, and representation of the stress term in terms of viscosity will be straightforward, and the equations, whatever we use, these are called as Navier-Stokes equations. Okay, but if we have some other complex fluid means non-Newtonian fluid, where value of viscosity is not constant, then for representing the relationship between stress and strain, we have to go for different type of fluid models, and our momentum equations becomes complex. Okay, so in this present course we will be referring our discussion only to the Newtonian fluid, so that's why we will be only dealing with the Navier-Stokes equations. Other important point is, whenever we have the governing equations, we try to represent governing equations in two forms, either integral form or differential form. Okay, so if you see, when you study the fluid mechanics, then initially you define your equations using the Reynolds transport theorem. So whenever we define initially using the Reynolds transport theorem, then we define the governing equations for finite sized control volume. So once we define for finite sized control volume, then equations are in integral form. The way we do thermodynamic analysis, all the thermodynamic analysis is mostly done in the integral form. Okay, but whenever we have to account for the individual variation of flow parameters within the control volume, okay, that what is happening at each and every point within the control volume, then we have to use the differential form of governing equations. Okay, and one assumption we make while we derive the differential form of governing equations in basic fluid mechanics, that whatever the control volume we have in hand, that control volume is of infinitely small size. Is this one clear? So all of you take some volume, something like this, and while we are considering the size, then we write dx, dy and dz. Okay, and we say that dx, dy, dz, we are using the sizes in order to refer that this control volume of infinitely small size. If I have to take control volume of finite size, then we write delta x, delta y and delta z. Is this one clear? Now, what is the limitation on the size of this infinitely small control volume? Do you know from your basic fluid mechanics? First point is very clear to us that it should be of smaller size. Why? Because for this entire control volume we will be defining some density rho, some velocity v. So the properties within this control volume should not vary. So that's why we have to take its size small. But it should not be so small that the assumption of continuum is not valid, because we are trying to define our governing equations only within the continuum approach. Okay, because if we go for sizes lesser than the Nunson number 1, in that case what will be happening? Molecular effects will be coming into picture. Okay. So you can refer to basics of fluid mechanics if you are finding difficulty in all these points. Okay. So now, what is our interest? Our interest is to write governing equations for multi-phase flow. So when we are writing governing equations for multi-phase flow, then in addition to the whatever the assumption we are making in single phase flow, we have to also make some more assumptions. Okay. So what are the assumptions? First assumption is that we have to use infinitesimal volume of dimension epsilon, but this epsilon should not be very much smaller than the typical distances over which the flow properties varied significantly, but also very much larger than the size of individual phase elements. What is the meaning of this? The meaning of this is, if you have taken a control volume, and within this control volume you have only, so this is your say dispersed particle. So in this case what is happening? My size of control volume is so small that it is not even able to enclose a single particle within it. Okay, so this type of control volume will not be a good representative of the multi-phase mixture. Okay, rather I have to choose the size of the volume in such a way so that this volume can enclose good number of particles in it. Okay, however, it should not be so large that it is containing significantly large number of particles such that the variation of properties from one point of the control volume to other point of the control volume is actually huge. Yes, yes. That is why we are writing equations for multi-phase pictures. Is this point clear? So, whenever we have to define the size, it should not be so small that a good representation of the multi-phase mixture is not there. Okay, and it should not be so high that representation of multi-phase mixture is there, but properties cannot be ascertained as invariable within the control volume. Okay. And why good number of particles should be there? Because ultimately we will be defining some combined properties for the dispersed as well as the continuous phases. So when we are defining the combined properties, then that property should be a good representative. So volume fraction should be in good ratio. Okay. It will be. I will show you how. Yes. Yes, initially we will start with this. So there what will be happening in case of separated flow, whenever you are referring control volume here and here, you need not to go for multi-phase equations. You can simply solve this using the single phase equation. But when your control volume is pointing near the interface, there you will be having the multi-phase mixture present. Okay. So in that scenario, the multi-phase equations will be applicable for only the control volumes which are holding the interfacial boundary, and for all other cases the single phase equations will be valid. No, so we actually what we do, we try to adapt certain ways, because here what we will be doing, while we will be defining these equations, based on the volume fraction we will be defining some mixture properties. Okay, so automatically if here and here volume fraction of one particular phase is becoming 0, then mixture property itself will take the properties of the single phase. Have you understood? So equation will be same, but depending upon the volume fraction, its mixture properties will be changing. So accordingly, it will be adjusting depending upon the nature of the volume fraction present. Is this point clear? Now, so what is necessary condition is to define derivative flow properties within the flow field. Second is that averaging should contain a good representative sample of each component. So already I discussed these 2 points. And averaging volumes typically contain finite number of finite sized particles. Therefore, the flow properties such as continuous phase velocity vary significantly from point to point within these averaging volumes. Okay, so for a volume, you can define the constant value of some value of mixture property. Okay. However, if you talk about flow properties such as velocity, that will be varying significantly. Because if you have finite size of different phase particles available in the system, then continuous phase will be having different velocity and the dispersed phase can have different velocity. Okay, so that's why velocity within this system varies significantly. This point I will not discuss at the moment. Last point I will discuss when I will give some idea about turbulence in multi-phase systems. Okay, now let's talk about conservation of mass equation for multi-phase systems. Okay, before this, can you tell me what is conservation of mass for single phase equation, single phase flow in differential form? Del rho by plus equal to 0. This is my continuity equation in single phase flow. What does this term represents? This represents the density change with time because it is written in on per unit volume basis. So if I understand this in per unit volume basis, then it represents the rate of change of mass within the control volume with time for a unit control volume. Okay, so it means this represents the changes within control volume. What it means? If within the control volume there is some source of mass generation or some sink which is actually capturing the mass. And what does the second term represents? Divergence of rho v. This represents mass change across boundaries of control volume. Is this point clear? So if you have a control volume, in your control volume there can be some generation of mass here if you have some mass source present. So whatever loss or generation will be there within the control volume, that is represented by first term, and other possibility can be some mass is entering here, some is going out, some is entering here, some is going out. So whatever the net mass change is across the boundaries of the control volume, that is given by the second term. Is this not clear? Now we have to one by one understand the each term. So this second term, if I have to write in tensor notation, I can also write it in terms of del rho vi divided by del xi. Is this point clear? So in tensor notation, this term can be simply written as del rho vi by del xi. What I have done over here? I have written a term del by del xi. First, have you understood from this to this how I can write? What is this? Divergence of rho v vector is nothing but del rho u by del x plus del okay. Now if I represent x, y, z with say indices x1, x2 and x3 and UVW with V1, V2 and V3. Then I can write this term as simply del rho Vi by xi, where I is varying from 1 to 3. Okay, so this is tensor notation. Is this one clear? Now, what does this term represent? Del rho n into j and I by del xi. So this term is identical to this second term of the conservation of mass equation. Is this one clear? The only difference is in place of velocity, what I am considering? Superficial velocity. Can you tell me why? When you calculate the mass flux across a boundary in single phase flow, across the entire boundary the same phase will be entering. Okay, across the entire boundary same phase will be entering. So it means total mass flow rate will be the density into velocity into area. Okay, but in case of multi-phase flow, what will be happening? At this boundary, there can be situation that along with the continuous phase, some bubbles are also entering. Okay, so once some bubbles are also entering, it means at this entire area, phase velocity is not applicable. Phase velocity will be only applicable at the corresponding locations. Okay, but which velocity is there, which we define based on the total area? The velocity which we define based on the total area for a particular phase is known as superficial velocity. Okay, so that is the reason whenever I am writing this boundary term, it is actually using velocity j and I. Is this point clear or not? This is important to understand. Okay, because if you take any boundary of the control volume for a single phase flow, the entire boundary will be filled with the single type of fluid. So that is the reason that rho into u will be coming into picture. But in case of multi-phase flow, at the boundary there can be some portion of other phases present at the boundary. So a boundary of a control volume is not completely filled with the nth phase which we are referring to. So that's why in order to take into account the effect or the difference between the phase velocity and the superficial velocity, because superficial velocity, despite the fact that what is phase fraction, it only accounts for mass flow rate over total area. Okay, so that's why I am using J and I over here. Is this point clear or not? So if this is clear, then if I have to write continuity equation for nth phase, what it will be? See, continuity equation is del rho by del t. But when I am having a multi-phase system, then nth phase is not fully occupying the control volume. Only alpha n fraction of this is occupying the control volume. So that's why del by del t of rho n into alpha n. Point is clear? Plus across the boundary I will be having del by del xi of rho n into j n I. Is this point clear? Now one important point is, within the control volume, I can have some phenomena like boiling. If boiling is happening and my nth phase is liquid, then what will be happening? Mass of liquid will be decreasing within the control volume. If phenomena is condensation, then mass of liquid will be increasing. So it means that as in case of single phase flow, there is no change of mass of a particular phase within the control volume. That's why right hand side was equal to 0. But in multi-phase picture, there can be loss or gain in the mass of a particular phase within the control volume. So that is the reason in right hand side I am using In, where this is mass source term for phase n. Is this point clear? What is In? In is mass source term for phase n. So if my nth phase is a liquid and boiling phenomenon is happening, then this term will be of negative magnitude. If my phenomena of condensation is happening and nth phase is liquid, then this term will be of positive quantity, because for condensation what happens? Vapor condenses and liquid forms. Okay, so there this term will be becoming of positive. Is this point clear? Yes, yes. But if I consider nth phase as vapor, then the mass terms will be of opposite sign. Okay. So this is just an example I am giving at the moment. Okay. So is this continuity equation clear? This continuity equation, because it is written only for a particular phase which we are designating as nth phase. So this is called as individual phase continuity equation. IPCE. Is this point clear? So this type of equation is called as individual phase continuity equation. We will stop now and we will discuss further in the next class.